There we go. Okay. Let's close this guy and let us cogitate. Okay. So we had talked earlier about challenges with subclassing as a component of challenges with type hierarchies in general. And going through Liskov substitution principle and talking about subclassing interfaces, we talked about a number of them. We also talked about class-based abstraction having this challenge with multiple inheritance, that it's semantically tricky and confusing when a given class can have multiple parents because you can have classes and names. You can also have common superclasses of those parents, and you've got to figure out how to deal with those in a principled way. And languages have sought to do that. If you look at the common list object system, way back in the 80s, I think, it tried to rationalize this. But basically, people realized that it's often a lot more confusing than it's worth. And one thing we discussed last time was the skeletal implementation. So the idea here is that we provide an abstract class in a language like Java, where we define most methods in the class, but a few of them are left abstract. What does that mean that they're abstract?
Not implemented.
They're not yet implemented. There's no implementation provided for them. So can we create an instance of abstract map entry? Directly? Can we say new? Cannot la. You cannot. Okay? That's not something you can do. It'll say basically these methods have not been defined. So what we can do is we can use these in several ways. Some of them are very familiar with you. You could create a class that extends that abstract class and fills in the remaining methods, right? These methods, get, size, set, perhaps are abstract in the superclass, abstract list, but we give the requisite implementations. Could we now, having given the implementations for all the missing methods, could we then instantiate, could we say new X list? Can. Yeah, we certainly can. Eh? Okay. Another thing we can do that we talked about last time is we can, within our Java code, we can just say, and this syntax is confusing to people because they say, wait a minute, you just said a few minutes ago, you can't say new abstract list. Well, this is not any old new I'm not creating a new abstract list in isolation. I'm actually creating with this begin curly bracket and end curly bracket after that. What is going on here? Is it instantiating something whose concrete class, whose actual type is in fact abstract list? No, we're actually creating what? An anonymous subclass of abstract list with these methods being provided, right? Being provided. And so if you see the syntax in code, don't be fooled by thinking we're allocating directly an abstract list and be thrown off by that. You're actually allocating an anonymous subclass of abstract list with these methods filled in, okay? That's also acceptable. It's just like this, except that we haven't, except that we haven't named this class. We're just not naming it. In this case, we're creating an instance of this anonymous class and we're returning it as a list, which is something abstract list implements. So we're just treating it as some implementation of list, the list interface. Does that make sense? Okay, so that's something we can do with a skeletal implementation. And by just an economy of mechanism, of filling in these couple methods, we can be off to the races. We can have an implementation. Here's another one, and this should give you a bit of thinking when it comes to multiple inheritance. So here, I have a class, XList, which formally extends one class. That's all we can do in Java, right? We only have the option of extending one class, not two. Zero, well, okay, we're extending Java.object always. but we're extending one class, and then we say we implement list. And so we got some class Y that we're a subclass of that I'm not showing. Okay. But then we say further we implement list, and internally we create a list delegate. And to fill this in, we create an anonymous subclass of abstract list. We fill in a few methods, just a couple missing methods from abstract list, just like we did here or here. We fill in the couple methods. That's exactly what we're doing here, and we call this list delegate. And then anytime someone calls on us one of these methods that is defined within the list interface, we just call off to this delegate that we created. We call off to this delegate. And I would argue that this class, while its beauty could still be refined, it functions as if it's an implementation of as if it's extended two superclasses. What are the two superclasses that it does a reasonable job of kind of extending here?
Y and list.
Y and, yeah, list is the interface, but abstract list. It's actually, let's be clear here. Why do I say it's as if it extended abstract list here? Yes, it's true list. It's implementing list. But remember, ladies and gentlemen, what does extending a class give us that implementing an interface does not? What does doing subclassing give us that or subtyping doesn't give us? Polymorphism. Okay, subtyping gives us polymorphism, and that allows us to pass around a B as if it's an A. So you're right that polymorphism is a feature that we get through subtyping. It's a feature we get through implementing an interface. That is, we get polymorphism. We can pass around ourselves as if we're a list. But subclassing gives us something more. What does it give us?
Additional implemented methods?
It gives us the implementation. Right? If we extend a class, not only can we pass it around as if it's an instance of that class, polymorphism, but we also get the implementation. We inherit, right? We inherit. If not the earth, we at least inherit the methods and the fields of the superclass, right? Probably better than inheriting the wind. So, ladies and gentlemen, when we subclass a class, we actually get its implementation as well. And remember, back a few lectures ago, we talked about the responsibilities that come with that. That I have to avoid breaking the functionality of that class, because now I care about what calls what in it. Remember that? Okay. And that class, if it evolves, I want to make sure my class doesn't break, my subclass. So with subclassing comes more than subtyping. With subclassing comes reuse of implementation. And I would argue that this class, XList, has a pretty passable ability to reuse the implementation of two classes. One of them is Y. After all, it's a subclass of Y. We get all of Y's good methods. All of the methods re-inherited. Okay? Inherited here. But beyond that, we get almost for free, not quite, but almost for free, the implementation of abstract list here. Because we're delegating systematically to list delegate. And we have to fill in a couple here, a couple missing methods. But otherwise, list delegate here has all of the other methods defined associated with list, except these three. We inherit, it got them through by taking this anonymous subclass of abstract list. And whenever one of those methods is called, one of the methods in list is called, we just delegate off to list delegate by if size is called with us, we call size on list delegate. Just if insert is called on us, we call insert on list delegates. If is empty is called on us, we call is empty on list delegate. And what that means is we don't have to re-implement all the methods of list. We've got most of the implementations through this. We just systematically delegate off to list delegate. And so in short, we've kind of, in a way, we certainly inherited the implementation of Y, and we've pseudo-inherited, we sort of inherited, we've quasi-inherited the implementation of abstract list. Yes?
So where it says return the abstract list with the parentheses, why
Oh.
are there parentheses? And does that mean there's a potential for parameters?
So why is there parentheses here? Like here?
Yeah.
Oh, because it takes nothing as a constructor. This is calling its constructor.
Oh, I see. Okay.
It's a syntax, but there's something very wrong. I thought you were pointing out another thing, which is grievously, I've done you an injustice. Ignore that return. I was engaged in frobbing behavior, and I should have eliminated. How do I get rid of this line here? Give me a second here. I want to get rid of the mumble. There. Okay. Okay. So here we go. There's no return. We're just saying list delegate equals this thing, and then whenever we get a method call for something in list, the list interface, we just delegate it on to list delegate. Is that okay? Okay. Yes. Question.
Is there a reason it has to be an abstract class? Couldn't it just be any implementation of list?
Correct.
Yeah.
Correct. Yes. So it could be any implementation of list. You're absolutely right. What this gives you a flavor of is that it's almost like we're inheriting, not quite, but it's almost like we're inheriting from both Y and abstract list in the sense that not only can we use their methods, but here we can actually implement several variants on them by implementing, say, these three methods. We've sort of tailored abstract list to our needs.
Okay.
And if it just said new, my list or something like that, you wouldn't get that sense. If it's not an abstract class, you wouldn't get that sense I've tailored it to my needs.
Yeah.
This is showing, because we can override a method of Y, and we can essentially override these methods conceptually of abstract lists, like get, size, and set, to customize them for our needs. So it's as if we're inheriting from both. Yes, Connor?
Since you're just making the second part a wrapper, you can do this regardless of it being abstract or not. You can
Yeah.
override a wrapper's methods as you want, just fine.
This is true. This is true. So there we would instead of defining them here in the brackets, in the braces, I should say, abstract list, each of those in the braces, we would the curly brackets. We would in the delegation area, like with size down here, we could just define it to do our bidding there, and that is quite true. So that's right. Here it makes it a little bit clearer that okay, right here I'm telling it to do different things. But the point is here that we're getting a little bit of the flavor of multiple inheritance without that diamond problem type situation. Okay, but so these delegation to skeletal implementations, you escape to a degree from the single parent constraints of single inheritance. You can kind of mix in different classes, and you can have, in fact, polymorphism across multiple interfaces. Can I pass this around, ladies and gentlemen? XList, an instance of XList. Can I pass around as a Y?
Yeah.
Can I pass around as a list?
Yeah.
Can. Yeah, you can pass around as both, ladies and gentlemen. So you get this polymorphism against multiple interfaces, and reuse a lot of code from abstract list or indeed from any other class. That's true. There are some disadvantages. You've got this kind of ugly wrapper code, and there's an explicit class that you have to create to sort of capture this abstraction. I have to create an X list or a Y list or what have you. Okay. So having said that, I want to introduce a more principled way of doing this, okay? And this is through the use of this idea that's been called mixins. And the term mixin, as I understand it, was originated based on ice cream parlor experience. That we go to ice cream parlors, and I don't know if they still have these, but you can get a flavor of ice cream, and then you can get these things that are, at some more gourmet ice cream parlors, you can mix in ingredients within it. So you can mix in M&Ms, or you can mix in, do they still have Jimmy's? No? Okay. You can mix in Jimmy's, you can mix, I don't know what else they mix in these days. Garlic? Or gummy bears? Okay, I ate garlic ice cream one time. I had jalapeno ice cream. That's really interesting. Not as interesting as a kidness, in my view. Okay, so ladies and gentlemen, mix-ins. The idea here is you get you get sort of a major type of ice cream, but you can mix into it different flavors, different things, kind of weave them together. Okay, the goal is to kind of mix in bits of functionality into your implementation, to draw from multiple sources for your functionality. And some implementations of mixins basically depart from polymorphism and subtyping. They're about mixing in implementations, not merely having subtyping relationships. Okay, so to give you a flavor of this, the idea here is we might have, and this is actually with skeletal implementations here. We might have an interface timestamped and another one serial numbered, and they each have some default implementation with them, and we create something that's a mixture of these, timestamped and serial numbered string. So it extends string, and then it implements basically both of these interfaces, timestamped and, in this case, I timestamped and I serial numbered. Okay, and in this case, it does so through skeletal implementation. So it extends string, it inherits all those, it implements these interfaces, and it does so by the sort of delegation that we've just seen. So internally, it creates instance variables that are one for this abstract timestamp, but create an instance of that, an instance of this abstract serial number, and it basically delegates to those. But it turns out that there's nicer ways of doing this in some languages, and one of the languages that supports nicer forms of mixins is in fact Scala. And we're going to be turning to a Scala focus on this here. So the idea here is that we might have some abstract class, and then we have two subclasses. For example, a string iterator on the one hand that extends this, a rich iterator that extends this. Rich iterator adds a method to it. String iterator specifically defines this class to have a type parameterization of a character here. And what we're going to be able to do here is we're going to be able to create classes here which basically mix together one class with a set of others. So here in the syntax in Scala is this, that we're going to say, we're going to create a class that extends this one with this. And you want to read it in that sort of way. It can go on for a while. It'll say with X, with Y, with Z. And basically you read it as it extends X together with Y, with Z. So you read it all at once. It's extending what results from all of those being mixed together. Okay? So we're going to see how we can use this syntax and this notion of kind of these traits to capture some of the effects of mix-ins without many of their disadvantages. And I'm just going to give you a brief glimpse at this today, and we will finish it up on Monday. Okay, sorry, Tuesday. Okay, so here we go. Mix-ins with Scala traits here. Okay. So the basic idea here is that traits are going to replace but generalize the capability of interfaces. Traits in Scala are going to allow you to provide interface-like functionality. They can be, several of them can be kind of used at once, just like you can implement, have a class implement several interfaces. But you can also provide default methods associated with this. So it provides some implementation reuse while sort of avoiding multiple inheritance, okay? And traits are going to be able to inherit from another class, but you can use them to kind of mix in functionality of several things at once, okay? And we'll come back to this more next time. There's somehow the formatting of this has gotten messed up. But this is the basic syntax that we're going to be using. So we're going to say something like val_foo, and we're going to say, okay, this is an instance of this class with this mixed in. And you'll notice what I'm doing here. It's a little bit different from what we saw just a minute ago. So a minute ago, I emphasized that we could create here for example, we could create a class which extends one class and mixes things in. Over here, what I'm actually doing is I'm creating an instance of a class that has things mixed in at runtime. So I'm not merely saying there is a class bar which inherits from foo with trait whatever, mixing them together. I'm actually saying create an instance of this with these things mixed in. Okay, so you mix in traits when allocating certain objects. Okay, and you can sort of layer these objects on here. So take a look at this. For example, we could say there's a class myExperiment that extends simulation experiment with visualizer with run logger. So here, this is a simulation experiment, but it has the capability of visualization, the capability of run logging. Okay, so it's not just any old simulation experiment, it has these added capabilities associated with it. Or I could create an instance of it. I could say this experiment is an instance of new simulation experiment with visualizer, with run logger, and sort of bring that functionality together at once in sort of an anonymous class type of way. So I'm mixing together the functionality of run logger, which knows how to log runs every time they occur for the experiment, with the visualization capability to visualize what's going on with the basic capability of simulation experiment. So here we have a main class, but we also are mixing in this functionality of visualizers and run loggers into that, and in fact doing so at runtime when we initialize the method. It looks like I have to display this only with PowerPoint, so next time we'll deal with this properly. But the idea here is that we will we'll see how we can use these traits to basically put into place functionality that's very similar to Mixins. It allows us to kind of add bits of functionality with each of these items onto the object being allocated or onto this class, while at the same time not having this diamond problem that we had with traditional multiple inheritance. And there's going to be a phenomenon which is going to be a bit freaky for you, probably the first time, called chaining of calls, okay? Where basically it's going to allow calling off to a given method to allow for a corresponding method to be invoked, not only on the main class that from which you're inheriting, but on each of the classes that are being mixed in. So, for example, my logger, it's extending the logger with timestamps and truncated and clonable. And if I call on that logger log, basically what will happen is it will go through and call it on each of these items that are being added in to the degree they define that. It can be added in, and each of them can basically put a bit of additional information in there. For example, timestamped will timestamp it with the current time. Truncated will limit it to a certain number of characters. And as a result, when you call log on this object, on a my logger, it will not only have what logger defines as logging, but it will have these extra features of timestamping, etc. It'll actually chain those calls together, whereas clonable might not define log, and so we won't call it on that.
So traits have a dependency on the interface, is that correct?
Traits actually expand under the surface to have an interface when they're translated into Java bytecode. But by themselves, if we have a trait here, we don't have to define them as directly implementing an interface. So for example, we could define a trait logged here, and it doesn't directly require us to define a corresponding interface.
But if you use truncated on
Yeah.
something that is a logger,
Yes.
right? Like you would only be able to use truncated on something
Yes.
that implements logging, correct?
That's right.
Okay.
That's right. Yeah. Yeah. So for example, console logger here, you have to extend log here, and there might be a truncated logger or a timestamped logger that would also extend log. Yeah. So that can be passed around accordingly. Okay. So we'll see this next time, but the idea here is to mix in this functionality in a way that's conceptually understandable but easily extendable. Okay, so we will see you next time. Thank you very much.